Hi everybody and welcome to another PAT Problems video. My name is Helena, I'm the Access and Outreach Manager for the Department of Materials here at the University of Oxford, and today we're going to be taking a look at question number 13 from the 2014 PAT paper. So let's have a look at what this question is asking. Okay, so in this question we are given a circuit which looks like this, and we're told that each of the resistors in this circuit have a resistance of the same value, which is R. We're being asked for the total resistance of this network of resistors, the resistance between points A and B. Okay, so for this question we're going to need to remember how to calculate total resistance when resistors are in parallel and when resistors are in series. So if our resistors are in series, we know that the total resistance, RT, is equal to R1 plus R2. So we're simply summing the resistances if they're in series. If they are in parallel, then we know that 1 over the total resistance is equal to 1 over R1 plus 1 over R2. So we've got the reciprocal terms this time here. Okay, so coming back to our network of resistors, we're told that each of these has a resistance R, so I'm just going to label that on my diagram like this. Now we need to figure out how to break this circuit up. Okay. So we've got sort of an upper branch here and a lower branch here, so that's a good place to start. So I'm going to focus on the upper branch here. And I'm going to calculate this little network here first, which I'm going to label as 1. So for 1, they are two resistors in parallel. So we know that 1 over R1 is equal to 1 over R plus 1 over R, which is equal to 2 over R, which therefore tells us that R1 is equal to R over 2. Okay, so if we want to then calculate the resistance of the top branch, R top, we have a network with resistance R over 2 in series with a resistor R. So we just need to sum those. So the resistance of the top branch is equal to R plus R over 2, which gives us a nice value of 3 over 2 R. Okay, so that's the top branch there. Let's now have a look at the second branch. So we've got a little bit more of a complicated network of resistors here. So I'm going to call this one number 2. Now we can already see on the top branch here we have 2 in series. So we can see that this is going to sum to give us 2R at the top. So now we have a network of resistors 3 in parallel. So for network number 2, we have that 1 over R2 is equal to 1 over the top bit, which is 2R, plus 1 over the middle one, which is 1 over R, plus 1 over the bottom one, which is 1 over R. So we need to do a little bit of messing around with our fractions here. So first of all, I can sum these. So we have something that looks like 1 over 2R plus 2 over R. Excellent. So if I then make the denominators the same, you can see that that is the same as 1 over 2R plus 4 over 2R. So I've multiplied the second term by 2, which if we group that together gives us 5 over 2R. And remember that's 1 over R2, so if we flip that upside down, we have that R2 is equal to 2R over 5. Okay, so that gives us a network with resistance of 2R over 5 here in series with a resistor R. So let's calculate the bottom. So the R bottom is equal to 2R over 5 plus R, which is equal to 7R over 5. Okay, so we've worked out our resistance for our top and bottom branches. So this circuit is equivalent to something that looks a little bit like this. So we've got a top branch, which we've calculated the equivalent resistance of, and a bottom branch here. And this top resistor is 3 over 2R, and this bottom one is what we calculated down here, which is the 7 over 5R. Excellent. So now these are in parallel, so we can use the reciprocal equation. So now we have that 1 over RT, which is total resistance, is equal to 1 over those two resistances. So we have 5 over 7r plus, remember the top one was 3 over 2, so we've got 2 over 3r here. So let's do some cross multiplying of our fractions. So we have that's equal to 15 over 21r plus 14 over 21r, which gives us a value of 29 over 21r here. And again, that's 1 over RT, so if we flip that fraction the other way around, we have that the total resistance of that network is equal to 21 over 29r, which we could turn into a decimal, but it's always nice to leave it as an exact fraction there. So that is the answer to this particular question and one way we could go about solving it. So I hope that was useful, and tune in next week for another PAT Problems video.